gas pressures, and we're going to do Dalton's law of partial pressures, which is the worksheet that you're going to do tonight, page 23, number 1 through 5. I'm not going to get through some practice problems on Dalton's law, so there's another short video attached to this Canvas module, which will have a couple practice problems. And then there'll be another module which will have practice problems for both Graham's law of effusion, Dalton's law of partial pressure, and also I will give you some conversion problems for the units of pressure, which we're also going to go over today. Okay, so there'll be some practice problems for the test, okay? For the quiz. Okay, so gases exert pressure on the container that they're in. Gases exert pressure on the container by colliding with the sides of the container. And this we talked about when we talked about the balloon. We talked about how the particles collide with the sides of the container and they keep the container open, right? The balloon open. So the next thing that we want to talk about is air pressure. And I'm going to give you a very, very, very simplistic definition of air pressure today. And then we'll talk about it a little bit more deeply when we come back. But air pressure is, for today, the pressure exerted by the column of air on your head. So there's this column of air that's sitting on top of your head and it extends down from the stratosphere, right? And there's basically two or three things that affect the mass and the weight of this column of air. The first thing is to think about is gravity. Gravity affects this column of air. How does it affect it? Well, if there's a lot of gravity, then there's many particles of oxygen in this column, right? Because they're all being pulled down to the earth, right? The oxygen particles are affected by the force of gravity, and they're all a lot of particles in this column, and it's very dense with particles, and they're being pulled down to earth because there's heavy gravity, right? But what if there's not very much gravity? Well, if there's not very much gravity, then there's not very many particles of oxygen in this column, and so the column is, let's say, what if there was only like 3% gravity? Well, then the column would be essentially empty because there would be no particles being pulled down into Earth, right? So there would be nothing in this column, right? Well, this is what happens when you go up to the top of Mount Everest. The top of Mount Everest is 30,000 feet, which is about 5 miles. So 5 miles away from where we are right now. We're about at zero, right? We're at zero. We are sea level. And Mount Everest is 5 miles above sea level. So 5 miles up. The difference between our gravity and the gravity at the top of Everest is so much that the oxygen content in the column is at about 40% of what it is here. The oxygen particle content in the column is at about 40% of what it is here, which is why as you're climbing Mount Everest, you have to stop at the stations along the way for up to a month at a time to get acclimated to the change in the oxygen levels. You have to stop and you have to camp and you have to exercise every day and you have to get used to the fact that the oxygen levels are dropping. And even then, as you're summiting and getting to the summit of Mount Everest, there are people still who wear oxygen masks because the oxygen level at the top of Mount Everest is so low. Because, a couple reasons, one of which is the gravity is so low up there. So does it mean you're bouncing around like you are on the moon? No, it doesn't. But it does mean it's easier to walk. It also means that, which doesn't really help you because you're so exhausted because you're like walking through snow, and there's so little oxygen in the column of air. So there's very little oxygen. You're huffing and puffing with every single breath because you're not getting enough oxygen. And on top of that, you're walking through this snow, you're exhausted, you've been climbing through this ice, it's a rough ride, and then there's very little oxygen. So the gravity matters. So in Tampa, we have greater gravity. And there is less on the top of Mount Everest. Now, I don't want you to get a picture that they're bouncing around like they are on the moon on the top of Mount Everest. They're not, all right? But it does make a difference in certain things, and we're going to talk about some of those things when we come back from vacation. So think about the Denver Broncos. The Denver Broncos are in a city which is declared mile-high city. Why? Because it's a mile off of sea level. Now, those football players are tuned into playing at a mile high, less gravity, with a lower level of oxygen in the air. Any team who is like Tampa Bay, who's playing at sea level, the minute that they finish their last football game, they are on a plane to Denver for their next game, where they get off and they spend the entire week trying to acclimate to being in the mile-high city. Because the amount of gravity, the amount of oxygen that they're going to have in the air for the next game in Denver is going to be far less. So they have to adjust. And even after being there for a week, only a mile high, let alone 5 miles high on the top of Mount Everest, only a mile high, even then, you will see them on the television in between plays with oxygen masks on. Because they're trying to catch up on the oxygen that they've lost during the plays, because the difference between here and Denver is so great that they'll be okay to play, but after a while, they might need to come out because the oxygen level is low enough that it's a big difference. Now, compare that to Denver coming to here. They wait until the very last minute to come here. Why? Because they get here, the oxygen level in the air here is so high, it's like their lungs are in Disney World. It's like their lungs are at Disney World. They get off the plane and they're like, this is great, right? Because they have so much oxygen that they have so much more energy. Yes? Do not vape. Vaping is like tearing apart your lung tissue. All right. It's not even just about, oh God. All right, next. So being the gravity is one reason for this air pressure change. Another reason is the length of that column. So think about the fact that if you're on top of the mountain, that column is shorter, right? Than the column is if you're at sea level. So the column on top of my head of air is 5 miles longer than the column is on top of my head if I'm standing on the top of Mount Everest. Because if I'm standing on the top of Mount Everest, the column is 5 miles shorter. So the length of the column of air also has to do with the air pressure. So there is lower air pressure in the mountains. And we're going to talk about that the effect of that when we come back, because it has to do with boiling point and temperature that your water boils at and everything else, okay? All right, let's talk about some units of pressure that we need to look at and we're going to be working in. The first is 1 atmosphere, which is sea level. 1 atmosphere is equal to 101.3 kilopascals. And so we have abbreviation for this. 1 ATM is equal to 101.3 kPa. Now, all of our pressure units are set to 1 ATM. So we also have 1 ATM is equal to 760.0 millimeters mercury. Now, millimeters mercury is for a barometer. That's where we would use that. 1 ATM is equal to 14.6 psi. This is pounds per square inch. So this would be used like in your tire, right? You'll see this written on the side of your tires. It'll say how many pounds per square inch your tire can have. 1 ATM is equal to 760.0 torr. Now, torr is for torque, which is a twisting force. A twisting force. All right? Okay, and so one of the things that you're going to have to do on the test is you're going to have to convert these units. So here's an example. If I wanted to convert 3, so where would these go if you're going to have to convert these? On your periodic table. You're going to want to put these onto your periodic table because you're going to need them to convert them, right? So if I want to convert 363 millimeters mercury, and I need to convert them to torr, right? I would do 760 millimeters mercury. Let's say I want to convert them to PSI or KPa, 760 millimeters mercury to 1 ATM, and then 1 ATM to 101.3 kPa. So this is just like any other conversion that you're going to do. Okay? Just like any other conversion that you do. Okay? Questions? So tomorrow we'll practice these, and I'll put some up online tonight, on Canvas tonight. It's not any big deal. It's pretty easy, right? Okay, the next thing is Dalton's law of partial pressures. Now, Dalton said that each gas in a container exerts pressure on the container as if it were alone. Now, what this means is if I had carbon dioxide in a container at 3 atm, and I had added hydrogen into the container at 1 atm, so the total pressure was 4 atm, the carbon dioxide would still be at 3 atm, and the hydrogen would still be at 1 atm. So the pressure of adding another gas does not change the pressure of the gas already in the tank. They sit in that tank as if there is no other gas in the tank. All right? So we have a formula for this. P1 plus P2 plus P3 equals the total pressure. We add them up. They do not affect each other. The other thing is that the moles of gas X over the total moles in the tank is the same fraction as the pressure of gas X over the total pressure. So the moles fraction is the same as the pressure fraction. So what that means is that I can multiply the moles of gas X over the total moles times the total pressure, and that will give me the pressure of gas X. So what does this mean? If I know how many moles of gas there is in the tank, and I know how many of those moles is carbon dioxide, and I know the total pressure that the tank has in it, I can calculate the pressure of the carbon dioxide. All right? By doing this. So let's look at a couple of your homework problems, all right? So a 250 milliliter sample of oxygen is collected over water and 760 pressure of torr. What is the pressure of the dry gas alone? Here's the pressure of the water. So what are you going to do if you're going to try and make the gas dry? Subtract the water, right? I mean, makes sense, right? So it's collected over water, and it's 760 torr. So you're going to subtract the water, because the water has a pressure, and so does the gas. This is the total pressure. The water has a pressure, and so does the gas. The two of them together. You want the dry gas alone? Subtract the water. Does that make sense? It's collected over water, so there's water and there's the gas. I'm going to subtract the water. Then I have just the gas. P1 plus P2 is P total. The total pressure is 760 torr. If I subtract the water, I have just the gas, right? A mixture of 2 moles and 3 moles and 4 moles and 5 moles exert a total pressure of 800 torr. What is the partial pressure of each gas? Find your mole fraction and multiply it by the total pressure, and that will give you the pressure of each gas. You know how many moles of each gas there is, so you find your mole fraction, and that will give you, find your mole fraction, and that will give you the partial pressure of each gas. Okay? Does that help? Okay. All right. So you probably can get 1 through 3 done if you start right now. All right. There'll be sample problems up on the online. Okay.